In this video, I wanted to talk about bolts. So this is a pretty lengthy section in the PE handbook, relatively speaking. Bolts are going to be under the joints and fasteners section, and then there's a subsection for bolts. So there's several different ways that you can load a bolt. You can have like two plates that are bolted together that are under like a shear force, and for this you would just have to solve for things like shear of the bolt, rupture, and that would be of the member. So if we look at it from the top, rupture would be if the member fails like along that line. And then the last one, there's two more. One would be crushing, and that could be of the member or the bolt. And this is just going to be your bearing stress. Then the last one is shear tear out. So again, looking at this top view here, that would be if we failed along here and the bolt got torn all the way out. And then another way that you might have to analyze a bolted joint would be like if you have a fixed plate and it's and then a bar is bolted, and then you have some load over here. To solve for these types of questions, you would have that your force at the ith bolt is equal to the moment about the midpoint. So you'd have to find your centroid of your bolt group. So the moment at the midpoint times r sub I, which is the distance from the centroid to the center of the ith bolt. And then you're going to divide that by the summation from I equals 1 to n of r sub I squared. Okay, and then the last thing is like if you have two members that are bolted together. I'm going to try to draw a better bolt on this one. Sorry. And then you have a nut on this side. So two members are bolted together like that. This is the type of example problem I wanted to run through today. But there's quite a few equations for this one. So the first is preload, which is F sub I. And the preload is, there's not an equation necessarily for it, but it's basically the clamping force of the bolt. It's how tight it is. And then generally speaking, with this type of loading, you'd have the member loaded and tension, and you'd be asked to solve for like the total load in the bolt or the total load in the members. And you got to do some mechanics of materials type thing here. So there's a constant called the joint constant, which is the stiffness of the bolt divided by the stiffness of the bolt plus the stiffness of the members. And then the total load in the bolt, or call it F, the resultant load is equal to your preload plus your load, the part of this applied load that is carried by the bolt, and that's going to be that applied load times your joint constant. And then for member, the resultant load on the member is the total load carried by the member, and then minus the preload of the bolt. So these are kind of, these equations aren't necessarily really intuitive. So it's good to know where to find them at. So just your keyword for this section is going to be bolts, and then there's a whole bunch of these equations listed out. There's also a whole bunch of tables in this section that you need to know how to find as well. So there, if you just search for the keyword bolts and then go a couple pages, you'll find some relevant tables. And one reason you need it is that a lot of times with bolts, instead of like stress being force over area, is force over the tensile area. And this tensile area is not something that you can solve just using like the radius of or diameter of the bolts. They account for like it being weaker at the threads, and so they actually reduce the area a little bit to account for that. But yeah, I have an example problem here to run through. And so 2 steel plates are clamped together using a single 1/2 inch 13 UNC grade 5 bolt. The joint is subjected to an external tensile load of 10,000 pounds. The bolt stiffness is 1.5 times 10 to the 6 pounds per inch, and the member stiffness is 4.5 times 10 to the 6 pounds per inch. The initial preload is 75% of proof strength, and then we're asked to determine several different things. So the initial bolt preload, the joint constant C, the additional load carried by the bolt due to the external load, the resultant bolt load, the factor of safety against proof strength, and whether the joint separates. Okay. So, like I said earlier, there's not really an equation necessarily for the preload, so we just kind of have to use our context clues. So it tells us we're loaded to 75% of proof strength. So I know that it's going to be 0.75 times proof strength. I'm just going to write that as S sub P, and then times that tensile area. Very important to use the tensile area for anything having to do with a bolt. So it's going to be 0.75 times our proof strength. Now, what is our proof strength? Well, it didn't give it to us in the question, but we have this table down here that should have it in it. So if we look at a grade 5 bolt, grade 5, and we have a 1/2 inch diameter, so we're going to be at this upper portion, our proof strength, and it doesn't say whether to use, or, sorry, I thought for a second that this would have a different, like, maximum proof strength, but this just has a minimum. So we're going to go with this 85 KSI. And then for our tensile area, if we come over to this table, we go down to the 1/2 inch bolt, and we go all the way over to this last column. We see our tensile stress area is 0.1419 inches squared. So if we plug this into a calculator, it's going to come to 9,046.125 pounds. So that's the preload on the bolt. That's how tight the bolt is. So now we're asked to solve for the joint constant C. So from this equation right up here, it's just the stiffness of the bolt over the stiffness of the bolt plus the stiffness of the member, and it gave these all to us. So the stiffness of the bolt is 1.5 times 10 to the 6. Since these all have a 10 to the 6, I'm just going to write the 1.5. And this was a 4.5 for the member stiffness. And they're all the same units as well, so the units are all going to cancel. It's just going to be 1.5 divided by 6, which is 0.25. So what exactly does this number represent? Well, the 0.25 represents like the more or less the percent. I guess it would be 25%. The percent of the load that is actually carried, the externally applied load that is actually carried by the bolt. So the rest of this other 75% is going to be carried by the members. So then for part C, the additional load carried by the bolt due to the external load. Okay. So if we look up here, the resultant force on the bolt is equal to the preload plus the load carried, or the load of the bolt due to the external load. So this is the only part that we're asked to solve for. So the force in the bolt, I'm going to call this P, so B is equal to C times P, which is going to be 0.25 times our load, which was 10,000 pounds. So the additional load carried by the bolt in addition to this preload is 2,500 pounds. Alright, and then for D, we're asked to find the resultant bolt load. So resultant bolt load is just what we found here, which is the extra load due to the applied force plus the preload. It's going to be 9,046.125 plus 2,500, which is 11,546.125 pounds. So this is the total force carried by the bolt. Includes both the preload, which would be due to tightening, and the load that the bolt carries due to an externally applied load on a member. Alright, and then E, the factor of safety against proof strength. So our factor of safety is going to be our proof strength divided by the actual bolt stress. So our proof strength was 85,000 pounds, which we got from this table, or sorry, PSI. And then for our bolt stress, we're going to use the total load that the bolt carries, which is 11,546.125 pounds, and divide that by the tensile area, which again, make sure you're getting that from this table. So it's going to be 0.1419. So we have factor safety 1.04. So that's pretty low. As soon as that hits 1, then that means our stress is at the proof strength. The proof strength is essentially the yield strength for bolts. Okay, and then for F, we're asked to determine whether the joint separates. So there's no equation for this in the handbook, so you got to kind of think it through. So let's just draw out what we got going on. So we have two steel members, and these are in contact. I just drew them separately just so it would be easier to tell that there are two of them. And there's a bolt going between the two of them. Okay, so that bolt is squeezing them together. But at the same time, we have this 10,000 pound force that's trying to pull it apart. So the actual clamping force that's holding those two plates together, so the clamping force equals the bolt preload. And then, so we need to basically figure out, is the load carried in the members greater than the preload? And if it is, then this joint is going to separate. So what is the load carried by the members? Well, if you remember from above, the load the bolt carries was C times P. So we know that the load the member carries is just going to be 1 minus C times P, which is going to be 0.75 times 10,000, which is 7,500 pounds. Our preload was this 9,046. So 9,046.125 pounds is greater than 7,500 pounds. So the clamping force is greater than the forces actually carried in those members. So it does not separate. But yeah, these questions aren't too bad, especially if you know how to use these tables, you have to know how to use the tables and make sure you use them right. The biggest thing, or the biggest kind of a pitfall, is not using the tensile area. Is trying to calculate that yourself just using pi r squared. That's not going to get you the right answer. But yeah, I hope this helps.